Today, we'll show how we can leverage the human ventral visual stream to improve neural network robustness. Deep neural networks have incredible performance on many visual tasks, such as the typical image classification task. But in recent years, they have been shown to have significant vulnerabilities. For example, even subtle image perturbations that are invisible to human eyes can trick them into mistaking this dog for an ostrich. And I can increase the magnitude of this perturbation to make the deep nets become more and more confident in their wrong prediction. But for humans, we would never call this an ostrich with full confidence. So this leads to a question of how do humans achieve such visual robustness? The key could be in the human ventral visual stream. In particular, one perspective proposed that the human representational space evolves as the object manifolds being pulled apart or disentangled along this ventral visual stream. And this disentanglement could be the key to robustness. So let's unpack this a little more with an example. According to this perspective, all identity-preserving transformations of an object, for example, this dog, should form a continuous manifold like this. So any changes that still allow us to recognize the dog, including this perturbed version here, should fall on this manifold. And of course, the clean image is just another high-dimensional point on there. And the same would apply to, for example, an ostrich. However, these are just ideal depiction of these manifolds nicely shaped like this. It can be much more complicated, especially in the raw pixel space. These two manifolds can be highly entangled, like two sheets of paper crumbled together, so we can't really tell them apart with a simple linear decision hyperplane. Now, what our ventral visual stream does is to transform these manifolds step by step to become these very separable ones embedded in the final good neural space. Since all identity-preserving transformations of the object are just different data points on there, being able to separate them would naturally entail robustness to any reasonable changes. But deep nets, perhaps with very different architecture and learning regimes, they do not develop the same strategy, and the final space could still be entangled. Unfortunately, exactly how this transformation works is still not entirely clear to us, so we can't directly translate the principles into model design. However, if this evolving space is indeed the key to human robustness, then perhaps we could consider feeding these neural representations directly into the deep nets, essentially encourage them to develop a more human-like space, and then perhaps human-level robustness will emerge. So this leads to our first point of investigation, that is whether we can improve model robustness if we simply teach them the human representations for each image they see. And then taking one step further, if we use representations from multiple stages along the ventral stream to guide the deep nets, then can we see hierarchical improvements, thus confirming this evolving representational space. And here we teach the deep nets with the method of what we call training with neural guidance. Okay, let's start by considering this standard REST identity architecture, here performing a classification task. And we're going to call this final portion here the task head. And then we add another neural head that's simply a fully connected layer with the same dimension as a human neural representation corresponding to the very same input image. So we can have this additional L2 loss here forcing the model to learn neural representation concurrently with the visual task. And of course, we'll have a hyperparameter alpha here to balance these two heads. And now the question is, how do we get these neural representation? So we took advantage of a recently released human fMRI dataset, NSD here, obtained from subjects viewing a very large selection of natural images. So now for each image, we have a corresponding neural activity pattern. But remember, we wanted to track the evolving representational space across the hierarchy. So we picked out 7 brain regions, or ROIs, at different stops on the ventral stream. We first have V1 and V2, and an intermediate area V4, and 2 consecutive areas, VO and PHC, on the ventral surface. We also picked out 2 areas on the lateral surface, intending to capture the shape-sensitive functional area LOC. Now, as we traverse these regions to guide the deep nets, we should expect a roughly hierarchical improvement in model robustness if better representational space is indeed achieved. One challenge we faced is that These neural data came from subjects viewing a very specific set of images, but we want to be able to use any number and any kind of images later in our experiments. So instead of using these data directly, we use this to train additional neural predictors that can give approximated neural responses. And of course, we train one for each of our 7 ROIs. So going back to our neurally guided model, instead of learning from these actual human data, this model learns approximated neural activity from these fully trained and frozen neural predictors. Okay, let's quickly summarize all the models we're going to evaluate later. There are 7 neurally guided models, each aligned to one of these 7 ROIs. And then 4 baseline models for comparison. First, we have a null model that's simply vanilla DNN with a task head only, no guidance at all. And then we have a random model with an untrained neural predictor. So this predictor only has randomly initialized weights, therefore the name random. And this condition can tell us if the extra head by itself can have any effect. We also have a V1 shuffle model with a fully trained V1 neural predictor, but during training, we pass different input images through the neural predictor and the main classifier. So essentially, we are pairing a raw neural representation to a given input image. And this can tell us if any neural characteristic data can lead to an effect, regardless of whether correct information exists in there. Okay, here's our V1 shuffle. We also have an additional TO shuffle with the same logic, but using a TO neural predictor just for comprehensiveness. So here are all the 11 models we included, and next I will go over how we evaluate the model robustness. So we focused on this adversarial robustness of deep nets, commonly evaluated using these LP-based additive adversarial attack. Essentially, we search for a particular perturbation to be added to the input image so that the deep nets will make a wrong prediction. For example, I'll switch here. And we can adjust the magnitude of this added perturbation by changing this epsilon here. Increasing the epsilon is essentially increasing the perturbation magnitude. Now, if our model is performing a typical ImageNet classification task, then the classification accuracy should decrease as the epsilon gets larger. And this example you're looking at here is the actual performance of our null model. Now, if any other models become more robust relative to this baseline, then we would expect an upward shift of this line. So let's first take a look at all the other baseline models. Now, surprisingly, they lie almost right top of each other. So guidance by random numbers or just neural characteristic data, noise does not make a difference. What about our neurally guided models? With V1 and V2, we've already seen some improvements. Even more from V4. Further improvements can be observed from the 2 ventral areas, and the lateral areas also bring more benefits. So we see that neural guidance does improve deep net's robustness, and more importantly, there is indeed a hierarchy of improvement as we use progressively later brain regions. I don't have time to show this, but we have replicated the same hierarchy across different data sets, different tasks, and different types of attacks. Okay, now it's time for the big question of why, or what is fundamentally different about these neurally guided models that made them more robust. One key property we looked at is the representational space of these models, using this representational similarity analysis. This is a very popular technique, so I believe many of you here may have already been very familiar with it. But briefly, we extract the activation pattern from the end layer of the model for each image, and then calculate the dissimilarity of all possible pairs using some distance metrics. And then we can plug these distance metrics into this matrix to capture the geometry of the representational space for this model. And we can do this for all the models we have and calculate the pairwise correlation of these distance matrices to produce this final representational similarity matrix. And here, darker colors indicate higher correlation and therefore greater similarity. You might also notice that we have some additional models here. Very briefly, these WD models are just deep nets trained with conventional methods to improve their robustness, but nothing neurally related. To help with visualization, I here provide this MDS plot. Each circle corresponds to one model, and the closer 2 circles are, the more similar their representational spaces are. So essentially, we see that all the neurally guided models, these red circles, developed qualitatively different representational spaces from all the other ones. And combined with our earlier results, these spaces are not only distinct, but also superior, in the sense that they in turn leads to better model robustness in the end. Okay, to summarize, we found hierarchical improvements in DeepNet's adversarial robustness with neural guidance from progressively later brain regions. Using RSA, we found that neurally guided DNNs developed very distinct representational spaces compared to conventionally trained and defended models. Yes. We actually performed more analysis to answer the why question, and we found, for example, they developed smoother output surfaces, and they started to make more shape-based decisions, both in the same hierarchical way. If you're interested in reading more about it, our paper is now available online. Okay, our work has at least two implications. First is that our results support the notion that the human visual robustness could emerge from this evolving representational space along the ventral visual hierarchy. And then these neurally guided deep nets also open up opportunities for studying these more human-like representational space, and then perhaps we can get more insights for the advancement of deep learning. Okay, finally, a special thanks to all my co-authors, and here's our funding source. And I'd like to thank everyone here for listening. I'm happy to discuss any questions you may have.
That was a really nice talk, thank you. My question here is, I'm just wondering if you fed the neural representation of the original object in the CNN back as a neural guidance, would you get similar results? And maybe what's really happening is just that you're giving back the original the representation of the original object in some way would improve robustness.
Good question. Thank you for bringing this up. The reason that we use like an intermediate neural predictor here is because we focused on classification task in the beginning. So we needed this like extra step to sort of translate from this NSD data, which is obtained from subjects viewing MS COCO, more like scene images, to ImageNet. I mentioned at one point in my talk that we have replicated this across tasks. So we have done one task that is image captioning. So that task can be done on MS COCO. For that, we also tried the original neural representation, and we see a similar results. Yeah.
Hi, great stuff, thank you. I was wondering if, you mentioned you had a different model for each region of interest in the brain. I was wondering if it could also perhaps work if you mapped those different regions to the different layers of a model, since they tend to sort of correspond with the hierarchy, and whether those models, if you have tried that, perform as well as the ones you showed.
Very interesting. This is actually in our next step list. So, yeah.
Okay, thank you very much.